Hi, so in this video for the Math271 final review video series, I'll be covering some theory for BVPs 1 through 7 and then going over some problems. So first here, I've outlined the theory that's required for the final exam, and this PDF will be linked in the description for this video so you can download it and have all these notes. But for now, I'm just going to quickly go over it. So first we have the derivation of the heat diffusion equation. So I've outlined it here step by step, how to prove this, how to derive it. And using the fundamental lemma, I stated that here. And to get to the Fourier diffusion equation, Poisson's equation, and the Laplace equation. I've also outlined the proving the uniqueness theorem specifically for the Robin problem. Noting that the other two can be found in your course pack, but I just went over the Robin problem. So here, again, going over the theory and to get to our final answer here. Next in this document, there's a review of BVPs 1 through 7. So first, you'll have the wave equation, vibration of a string, vibration of membranes, when to use the different types of equations, and then I go into defining the form for each of the BVPs and steps on how to solve. So BVP 1, that was the diffusion of heat in a thin bar. It has this form here. We know that there are two different types of conditions that we can get, the homogeneous Dirichlet or homogeneous Neumann, and we have the physical interpretation, and we know that in order to solve this, we need to use separation of variables. So like I said, this document just basically outlines all the steps on how to solve the different BVPs and the physical interpretation as well as the form. So here we can see BVP 2. Again, for BVP 3, that's with the rectangular region. Here's the steps to solve it. BVP 4, that's the circular region. Steps to solve for the general solution, and then dividing it up into the different kind of BVP 4s you're going to see. So we have A through E, different types of problems that you might encounter, and then how to modify the general solution to each of these specific problems. Now for BVP 5 and 6, I noted it a bit differently than what you might seen in class. So this is just how I split up BVP 5 and 6, but your class notes may have done it a bit differently. So here we have the form of the diffusion of heat of a thin bar being heated with generation or absorption term, so that Q term. And there's three different types that you might encounter. One is the homogeneous PDE with non-homogeneous boundary conditions. One is the non-homogeneous PDE with non-homogeneous boundary conditions. And the final one is non-homogeneous with homogeneous species. So those are the three different types. And again, steps on how to tackle each one of these problems. BVP 6, I noted it as the vibrating string, taking into account gravity. And then finally, BVP 7 is the steady state distribution in this cube region here and steps to solve. So here you can see that there's a flow chart for solving BVPs 5 through 7 that's created. So here, this is just an easy way of how to tackle BVPs 5 through 7. Following a series of questions, you start with your BVP of this form here, where G is your non-homogeneous PDE term. And once you'll start here and, follow the tree, and it'll tell you kind of how to tackle the different types of problems, whether you have Dirichlet or Neumann, what if you have non-homogeneous or homogeneous PDEs. This is kind of a way of how to solve the different types of problems. So you can take a screenshot of that if you'd like. And we're going to be using it to tackle our first problem here, which is derived from the course pack, problem set 5, question 5. So it's really similar to that problem. And it asks us to find the temperature distribution of a rod of length pi if n's are maintained at 0 and the initial temperature is x. Heat is generated in the bar at a rate of x e to the 2t, And for simplicity, let alpha squared equal 1. So this question is really similar to question 5. I just changed, I think this was x minus x squared, and instead I just left it as x for simplicity, and I added a generation term in terms of both x and t. So just changing it up a little bit, and here we'll see the solution to this. So first, what we want to do is to figure out how to solve this problem. So we have the steady state temperature distribution in a bar, and that is the general form of the equation here. So for this problem, we know that alpha squared should equal 1, and we have that our heat generation or absorption term is actually a function of x and t, so it's equal to x e to the 2t. And the question stated that the rod is of length pi, so we know that here L should be pi. So just setting up our PDE, it'll be of this form here, where x varies from 0 to pi, and our two boundary conditions, because the question said that the ends are maintained at 0, we will have when x equals 0 and x equals pi, those both ends are equal to 0, whereas the initial temperature in the bar is going to be x. So when time is 0, the temperature distribution is equal to x. Now, in order to solve this type of BVP, we're going to use that flow chart. So first, we know that we have a non-homogeneous PDE and we have homogeneous boundary conditions. So if we just take a look, we start with our BVP question. Are the boundary conditions homogeneous? Yes, they are. Is the PDE homogeneous? No. Then we look at our non-homogeneous PDE term. So that was our Q. Is it equal to some function of phi? No. Is it a constant or just a function of x? No. Then we move down here. It is a function of both x and t. And therefore, to solve this problem, we're going to want to use variation of parameters. So using variation of parameters, because we have the Dirichlet boundary conditions, so because Dirichlet, we are going to guess that phi is equal to the sum of Cn of t sine n pi x over L. So that is when we have a Dirichlet boundary conditions and we're dealing with variation of parameters, this is the guess that we're going to use. So what we need to do, we're just going to plug it into the PDE. So that'll give us and here we note that our L, our length here, is actually equal to pi. So the sine term here is just going to be nx. So then we have that second term. And that is all equal to x e to the 2t. Okay. So now the next step we want to do is we want to take the inner product, both sides, with sine of kx to solve for Cn. And so we know that this is just the same as multiplying both sides by sine of kx and integrating from 0 to L. So here we're going to have sine of nx times the sine of kx. And that will all be equal to the integral. So here, like I said, I just took the inner product of both sides and integrate from 0 to L. So that's how we try to find our Cn of t here. So we know that this is 1/2 the Dirac delta here, Kn. And so all we need to do is to solve this side. To solve that side, we're going to do integration by parts. And we're going to let u equal x and dv equal sine of kx. So just looking at that integral here, we're just going to do it down here. So this e to the 2t, we can bring that on the outside, 0 to pi, x sine kx, kx dx. And integrating by parts, we'll have e to the 2t, all in brackets, 1 over k, negative x cos of kx minus k times the integral negative over k cos kx dx. And that is all evaluated from 0 to pi. So this is just doing integration by parts. Yeah, so from there, okay, this stays, and then carrying out that integration, we'll have sine of kx, and then that's evaluated from 0 to pi. So now we know that if we just plug the boundaries in, we'll have e to the 2t, 1 over k times 1 over k sine of pi k minus pi cos pi k. So that is with computing our boundaries, the 0 to pi. And we know that sine of pi k is just 0, and then cos of pi k will be negative 1 to the k. So this simplifies even further to e to the 2t negative pi over k negative 1 to the k. And then if we just bring that negative term into our minus 1 to the k, we just simplify it down even further, the k plus 1. All right, so this was just the integration by parts. And I know it's tedious work, but in order to get to the solution, sometimes you're going to have to do this. So it's just important to get this practice in to know how to do these types of integrations that might come up in an exam situation. So coming back to our expression here. So remember, we were up here with this integrals on both sides. We multiplied it by sine kx, and we have that L over 2 Dirac delta. So coming down, we have L over 2 would be pi over 2 k over dt plus k squared ckt equal to the function we just found. So e to the 2t. And now, just bringing terms to the other side. And we are going to let k equal n for simplicity. So you could leave it as k, but we're just used to seeing n's and dealing with, sum of n equals 1 to infinity. So just I like to put everything back in terms of n. And it's just changing the letter. So it doesn't really do much to the equation itself, just changes the letter. So we'll have, all right. Okay, now that we're here, we notice that this is a first order non-homogeneous ODE. So in order to find our C of n, we're going to want to solve the first order and the way we do that is we apply the integrating factor. And so in this case, we just take whatever in the position in front of your term there that's not differentiated, and set that to the power of e. So in this case, it's just going to be e to the n squared. T is our integrating factor. And all we do is we multiply by both sides. And then by using the integrating factor, we can let the left-hand side simplify down to this. So the integrating factor times our variable. And then the other side becomes this. All right. So now that we're here, all we need to do is integrate both sides. And so we can bring this out of the integral. Oops. Sorry. So now here we'll have so this is if we carry out the integration in the denominator. And then we'll have an integration constant, and we're going to call that Cn of 0. All right, so now if we just bring the e to the other side, we're left with this. So the next step here is to plug it back into the PDE. So we'll get Now all we need to do is to apply our initial condition. So if I plug in t is equal to 0, I'm going to get this. And we know we can model this as a Fourier sine series. So we will have and we know we can just solve this using integration by parts, which we did earlier. And that led us to and so we can solve for our Cn of 0. And that would be all right. So there. Now we can just write down our final answer. So we had our Cn term plus our C naught term. And that C naught, remember, is multiplied by the e to the negative n squared t. And then all of this, doing square brackets, is multiplied by our sine term. All right, so that's the solution to this problem.